everyone, I'm Hui Tan. Today I will talk about my recent work. These are the contents I will present. As we know, the success of deep learning relies on a large amount of training data. Collecting and annotating data for all domains and tasks is extremely expensive. We can tackle it with data-efficient learning, such as semi-supervised learning (SSL). This work falls into the field of SSL. Here is the problem definition of SSL. Given a small labeled set and a large unlabeled set, SSL is to predict class labels for unseen test samples by learning a classification model, which stacks a classifier on top of a feature extractor. Next, I will briefly introduce the related works in SSL literature. Except those meta-learning-based approaches, existing methods can be divided into three categories: self-training, consistency regularization, and technique combination. For unlabeled data, self-training uses the pseudo-labels predicted by the model itself to supervise the model learning. Consistency regularization enforces the consistency of network predictions between an input sample and its perturbed counterpart. Recent advances are achieved by technique combination. For example, fixed match is a simple combination of self-training and consistency regularization, which trains the model on the strongly augmented version of a sample with the prediction on its weakly augmented version as the pseudo-label. Recently, flex match and co-match further improve over fixed match. The two techniques of self-training and consistency regularization would be uninformative if the model predicts a uniform distribution over classes for unlabeled samples. To address it, existing methods adopt confidence filtering, which abandons the samples whose prediction confidences are lower than a predefined high threshold. It is reasonable that the least confident samples are extremely unreliable. But are all the moderately confident samples useless? Is there any way to pick out the useful ones? We summarize our main contributions here. In this work, we solve the questions by introducing a novel framework of Taylor expansion-inspired filtration (TIF). The Taylor formula of the cross-entropy loss function with respect to the feature of one sample with true or pseudo-label mainly includes terms of the multiplication of gradient and feature of finite orders. To make the change of loss consistent in the neighborhood of the feature, this framework selects the samples of moderate confidence, whose feature or gradient is similar to the respective one averaged over the labeled and highly confident unlabeled data, which are the most reliable. In essence, the samples with similar local manifolds are selected. Hence, the final network update is still close to the one determined by the most reliable samples and further incorporates the new information contained in the selected samples of moderate confidence, such that the model optimization could be steady and improved. From this framework, two novel filters are derived to select the helpful samples from the moderately confident unlabeled data. The selected samples together with the highly confident ones are then used to train the classification model. The first filter based on gradients assumes that one moderately confident sample is useful if it follows the optimization dynamic of fully supervised learning. We can approximate the optimization dynamic by class-wise majority gradients, which are computed on features of the labeled and highly confident unlabeled samples. From those moderately confident samples, we select the ones that have similar feature gradients to the corresponding majority gradient. We thus term this method as gradient synchronization filter (GSF). The second filter based on features assumes that one moderately confident sample is useful if it has a certain level of prototypicality. The samples near prototypes are selected from those moderately confident unlabeled data. We thus term this method as prototype proximity filter (PPF). Here is the setup in our experiments. Following are our ablation studies, such as moderate confidence bounding, gradient synchronization thresholding, sample selection ratio, visualizing mislabeled ratio, and saliency map visualization. Our methods outperform the current state-of-the-art on widely used benchmark datasets. All experiments verify the effectiveness of our methods. More comparisons and analysis are provided in the supplementary material. That's all. Thank you.